Hey everyone, welcome back. In this video, we will introduce discrete distributions and some ways to describe discrete distributions, specifically expected value and variance. So we'll start by again discussing random variables in this discrete context. We'll introduce what are called probability mass functions or mathematical representations of probabilities associated with a particular outcome of a random variable. We'll then talk about expected value as a measure of center, and then variance as a measure of spread of the random variable. So first, let's reintroduce random variables. Again, these are real valued functions defined over some sample space that identify numerical events that are of interest. For example, if we want to measure how many people walk down the hallway during a class, that would be a random variable. The values are the counts of the people walking by. Discrete random variables are those that assume only a finite or countably infinite number of distinct values. In other words, when we have a discrete random variable, we can fully list the possible outcomes. We'll use capital letters like capital X, capital Y to denote the random variable, and again, lowercase letters like little x, little y will denote the observed value of the random variable. So for discrete random variables, the probability that capital Y, the random variable, takes on a particular value, which we will denote as the probability that y is equal to little y, is defined as the sum of the probabilities of points in the sample space S that are assigned the value y. We'll denote this function as little p of y. This is a probability distribution for a random variable. So this describes how the probability is distributed across all possible outcomes. This probability distribution can be represented as a formula, table, graph, just depending on what the random variable looks like and the values that it can take on. There are some properties that need to be satisfied. First, this probability of y must be greater than or equal to 0 for this to be a valid probability distribution. Another term for probability distribution is a probability mass function. So think of each point y or each outcome y as having its own little mass or chunk of probability. I'll abbreviate these as PMF. For probability mass function. So let's take a look at an example. We have a supervisor at a manufacturing plant who has 3 men and 3 women working for him. He'd like to choose 2 workers for a special job, kind of an easy, cushy assignment. Not wanting to show any biases, he decides to select the 2 workers at random. So we'll let y denote the number of women in the selection, and we'll find the probability of y. So to make this a little bit easier, I used R to list all of the possible results. Here I have the workers that I have selected. I've given them generic names, so Aaron, Brian, and Danny are the male workers, Jesse, Kayla, and Maddie are the female workers. There are 15 possible ways to randomly select 2 of them. Next, for each of those 15 ways, we want to count up how many women are in each pair. So for example, the Aaron and Brian pair, Aaron and Danny pair, no women. If I pair up Aaron with Jesse or Kayla, there's 1 woman on the task, etc. We could just as easily count up the number of men assigned to the task as well. So then, once I had that list, I counted up how many times or how many pairs had no women assigned to the task, 1 woman assigned to the task, and 2 women. And then that resulted in our probability distribution. So we can represent it with this graph or in the table. So the probability that y is equal to 0 is 0.2, probability that y is equal to 1 is 0.6, and the probability that y is equal to 2 is 0.2. So following that, we have a few theorems and results for this video. And here's the first theorem. For any discrete probability distribution, the following things must be true. First, the probability of y is bounded. It must be between 0 and -1. Or 0 and +1, That is inclusive, so the probability can be equal to 0. It also can be equal to 1. Second is that the sum of all of the probabilities must be 1 when the summation is done over all values of y. These properties should look familiar. This is a simple restatement of the axioms of probability. Now, keep in mind as we go throughout that these probability distributions that we derive are models for the frequency distributions of the population. So they're not exact representations, but a lot of the distributions that we'll see in subsequent videos are really good approximations of what might happen in practice should certain conditions be satisfied. Okay, so let's next introduce some tools that we can use to help us describe these discrete distributions, namely expected value and variance. So we'll start with the expected value. We'll let y be a discrete random variable with probability function p of y. Then the expected value of y, which we'll denote as capital E of y, is defined to be the sum over all the values of y of the value of the random variable times the probability that that value would occur. So that's the sum over all y's of y times p of y. If p of y is an accurate description of the population distribution, then the expected value can also be called mu, which we typically will use to represent the population mean. Think of this expected value essentially like a weighted average. The values over the long run with higher probability will occur more frequently. So we're weighting the possible y's based on their respective probabilities within the sum. So let y be a discrete random variable again, and let's say that we have a now function of y, say g of y. It turns out that the expected value of this function g of y is just the sum of all of the g of y, so all of those functions evaluated at y times the probability. So we can find, for example, say the expected value of y squared by summing up y squared times the probability. Now let's define another measure to describe our distributions, which we'll call the variance. So the variance is a measure of variability. So this tells us how spread out our probability distribution actually is. So if y is a random variable with mean mu, the variance of y is the expected value of the quantity y minus mu squared. A measure of variability that you may be familiar with already is the standard deviation. Standard deviation turns out to be the square root of the variance. So they are pretty nicely related in that way. The standard deviation then tells you the typical distance between a randomly selected value and the mean mu. We will denote the variance as sigma squared and the standard deviation as sigma. So we have a probability distribution for a random variable given below. We've got 4 possible values for our random variable y, corresponding probabilities. Here's what we'd like to do. We'd like to find the expected value, the variance, and the standard deviation, as well as graphing this distribution. Let's start with the expected value. So the expected value is going to be the sum of all of the individual values of y times their corresponding probabilities. So the expected value is 0 times the probability of observing a 0, which is 1/8, plus 1 times the probability of observing a 1, which is 1/4, plus 2 times the probability of observing a 2, which is 3/8, plus 3 times the probability of observing a 3, which is 1/4. So we get our expected value to be 1.75. Now to find the variance. The variance is really just the expected value of y minus mu quantity squared. So we'll calculate for each possible y, the quantity y minus mu squared, multiply that by the corresponding probability. So we get 0 minus 1.75 squared times the corresponding probability, plus 1 minus 1.75 quantity squared times the corresponding probability, and so on. All the way through, we get our variance to be about 0.94. Looking at what this distribution looks like, the expected value is 1.7. That's going to be right in the middle, somewhere between 1 and 2. Weighted a little bit more heavily toward 2 because that 2 has a higher probability of occurring than the 1. There's more probability on the right-hand side of the plot. How would we find the standard deviation, which is not on the slide? Well, the standard deviation is the square root of the variance, so we would just need the square root of 0.9375. Okay, so here are some results that will help us calculate things like expected value and variance. So let's let y be a discrete random variable with probability mass function, or PMF, P of y. C is going to be a constant. It turns out that the expected value of a constant is a constant. Right away, that should make sense. The probability that a constant takes on its value is 1. So that's a very straightforward expected value to calculate. The expected value of a constant times a function of y is just the constant times the expected value of the function. So constants can be pulled out of that summation. And then finally, the expected value of the sum of a set of functions is just the sum of those expected values. So we can distribute sums across these expected values. Here's one more result that turns out to be incredibly useful for us. I'm going to let mu represent the expected value of y, just to simplify the notation a little bit. Then it turns out that the variance can be written like this. The variance is the expected value of y squared minus mu quantity squared. This is known as the computational version of the variance formula. The reason for that, this form is a little simpler to compute by hand than this form. Okay, so let's use the computational form to find the variance of y. We already know what the variance is, but let's just see if we can make this a little bit easier. First, we need to find the expected value of y squared. So in our summation, we want to add a squared up here. So our expected value of y squared is 0 squared times its probability plus 1 squared times its probability, and so on. So our expected value of y squared is 4. The variance then is the expected value of y squared minus the expected value of y quantity squared. So we get 4 minus 1.75 squared, again 0.9375. So this does indeed work. All right, let's take a look at another example. We have a manager at an industrial plant who's planning to buy a new machine of either type A or type B. We're going to let T denote the number of hours of daily operation, T for time. The number of repairs required to maintain a machine of type Y is our random variable YA. It has mean and variance both equal to 0.1 T. Number of daily repairs YB for the machine of type B has mean and variance both equal to 0.12 T. We have also the daily cost of operating for both machine A, we'll call that C sub A, and machine B. Let's assume that the repairs take negligible time, so they're done very quickly, just exchanging a part, and that each night the machines are tuned so that they operate essentially like new at the start of each day. Which of these machines minimizes the expected daily cost over a series of workdays, or over the time of the workday? Well, here's what we're given. We know that the expected value and variance for machine A is 0.1 times T, which is the number of hours it's operating. Machine B has a little bit higher expected value, a little bit higher variance. We need to, in order to evaluate these costs, get the expected value of y squared. We have the expected value of y, and we have the variance, so we can tweak that computational variance formula just a little bit to help us out. So the expected value of y squared can be written as the variance plus the expected value quantity squared. So expected value of ya squared, we get to be 0.1 t plus 0.01 times t squared. For expected value of yb squared, we get 0.1 t plus 0.0144 t squared. Now to find the expected daily cost, well, we have constants, so we can pull those constants out. With respect to our random variable, t itself is a constant. So the expected value of 10t is t. Expected value of 30y squared is 30 times the expected value of y squared. After a little bit of algebra, we get the expected cost for machine A to be 13t plus 0.3t squared. Same line of thinking for machine B. The expected value of the cost is 8t times plus 30 times the expected value of y squared. So we end up with 11.6 times t plus 0.432 times t squared. Now, if we wanted to know which machine was more expensive to operate over a given amount of time, we could certainly calculate this by hand, but that's boring. So here's what I've done. I've written a very short R script to calculate the expected cost, CA for machine A, cost for machine B, based on t being a series of integers from 1 to 20. I've then created a data set with those variables and then used the ggplot function in R to create a plot. So here's my picture of the expected cost to operate each machine over time. You can see that there's really not a lot of difference between machine A and machine B. In fact, right at about 10 hours, the expected cost ends up intersecting. It becomes very, very similar. However, over time, the machine in red becomes a little bit more expensive to operate than the machine in blue. So that is it for this video. In the next few videos, we will begin touring or exploring some common discrete distributions. See you then.